We can go ahead for the next meeting, next talk, sorry, with Dr. Abdellatif Bouchalkh from the Technology Innovation Institute, and he will talk about laser drilling progress and challenges. So I give you the floor, Abdel.
Thank you, Dr. Guillaume, and welcome everyone to the Directed Energy Research Seminar. Glad to see everyone sharing all our knowledge and research. So I'm going to share here my slide. Okay, thank you very much. I'm going to be presenting some recent developments and technology that made it possible these days to reconsider laser drilling. And so we'll talk about these progresses and challenges as we go. And I'll start first by just giving you a quick review of some of these challenges and as an introduction, and then look at some resolved and unresolved issues, and then basically consider theoretical models that being used in this area without going too much into the development of the mathematical formulas. And I will go mainly in talking about the system design, the laser drilling system design, because really we have the intention to build such a system in TII, mainly to bridge the gap between the fundamental research and the industrial applications, especially with our big oil company here in the region and the challenges that are faced in the oil industry. So as an introduction, historically the laser drilling was considered since the 90s, and some tests were done in laboratories using the available laser sources at the time, such as the CO2 laser and indium YAG laser. But these are very bulky and also require a lot of power, electrical power, in addition to heating and other effects. So this was mainly limited to laboratory tests because you cannot deliver such laser beams at very long distances with the limited fiber optic development at that period. Very high powers were then achieved later on using different solid state lasers, and mainly quantum waves and fiber lasers, and that made it possible to have high powers and also be able to transfer the power to long distances, basically, which is required for drilling. So why do we consider laser drilling? Well, mainly for really very high efficiency, as well as the precision. As you know, we use it in many industrial processing because of the precision. So drilling oil wells also requires very high precision in drilling the wells with a very precise diameter. In addition to that, you save a lot of money on the steel pipes that you have to put after drilling, which is what we refer to as casing. And those can go for several hundreds of meters. So that's quite a lot of money involved. When you do laser drilling, basically you are melting the rock, and the rock is kind of creates for you that casing, basically to protect the land from sliding into the well. So this is a lot of savings if all the technology is possible to do. Now, still there are some challenges, and of course there is some tests that I will be talking about in the presentation. In addition to that, the flexibility of lasers is allowing to be able to drill not only in a straight line, but also in a curved and horizontal lines, as well as deep in the oceans. As you know, there are a lot of oil wells, or at least reserve oil fields, under the oceans, and to reach that is quite difficult with the traditional drilling methods. And laser drilling will really be able to be advantageous in this kind of drilling, where you can deliver the power through a fiber to different places in a flexible way. So these are advantages that are really pushing for developing this technology further and bringing it to a higher level of application in the industry. Now, there are only very few startup companies that are trying to use the laser drilling technology, mainly in drilling for thermal waters and very little attempts for oil fields. But there are plans to do that in a very near future, according to some companies. This really opens up a lot of opportunities for research and development as to make this technology more ready for the application in the oil industry, especially for rock drilling. So the opportunities are there, innovation is there, and the technology transfer is really encouraged, and definitely the market is really willing to look into this if it is possible to do with a lower cost. So we look at historically here just a few announcements in the media, as you can see here, since 2001. Laser as next generation drilling, National Driller. 2002, laser drilling put to the test. 2003, laser into the future. So a lot of, if you like, advertisement and hope for this to be applied very near future, but it's been 19 years now, and we haven't seen really a lot of it applied. Mainly for some challenges related to laser sources and other issues that I will discuss. Some of them are resolved, but others are still in the process, and eventually we will reach that with more research and development. So these are recent announcements in 2012, high power lasers. Fiber lasers drilled for oil. So this is really at the time when fiber lasers are able to produce much more power than any other sources, which really puts it in the perspective for application in oil drilling. So where are we now? Well, some of the issues are resolved, like I mentioned, and others are still not yet resolved and under research. Basically, laser will vaporize rocks, and this leads to the production of very high pressure gases. These pressure gases need to be evacuated, so this is something that needs to be considered. In a standard drilling, normally you have a fluid that you push, and while you're drilling, you can pump the fluid, but now we're dealing with gases and particulates. So this is another challenge that requires a delicate process to be able to deal with it. Laser sources also had some issues initially due to heating, and because the sources mainly use in very localized areas in the semiconductor to produce high power, and that requires attaching to the semiconductor materials that may not be suitable with different characteristics that will create stress, which affect the laser power, of course. So this was really a limitation with diode lasers and solid state lasers pumped with diode. In addition to the path of the laser in a solid state laser, it's very limited length. So the fiber optics high power fiber optic lasers really opened up this issue and allowed to resolve some of these problems. So delivering the laser at long distances has been a challenge for many years, and some companies now have developed very high efficiency high power fiber optics that allows to go long distances up to a kilometer or so, which is something that can be readily applied in the oil field drilling with lasers. The other big challenge, which is still an issue and is still a challenge today, which is the diameter of the drilling of the well. As we know, the laser is generally focused and the diameter of the laser is very limited, few centimeters or less, and the laser well diameter needs to be at least between 10 and 20 centimeters. So this is something that several researchers are looking at and trying to figure out different options, which we will discuss later. Optics, of course, when you are doing drilling with lasers, you're basically focusing laser, you are using optics, and we know optics are very sensitive to dust. Nevertheless, to consider plasma and hot particulates. So this is also a challenge to be able to evacuate all this dust and plasma fog that will be around the area of the drilling. In addition to that, of course, the harsh environment that we find at very deep wells where the temperature is very high and the pressure is also very high. So looking at just briefly the energy distribution, or how this energy coming from the laser will be distributed or used in the system. As you know, we are drilling a rock, so this is a kind of a mixture of many different materials. So you have energy that will, some energy will go to the hydration. So if there is water or some kind of fluid, a lot of energy will go into that before you start drilling. And of course, the melting, which is what we want. And then you have vaporization of the material, of the rock. Some of the energy will go into decomposition, and some of it will go to expansion and breaking the rock and making cracks. And these are all processes that need to be considered simultaneously. So theoretically, we cannot consider all these challenges and couple them all together at once. So the numerical methods are very limited in this area, and generally what is used is finite element methods or particle in a cell method that is commonly used in this area to treat plasmas that are produced. Monte Carlo simulations also to look at some of the statistics of the reactions that's happening. So I will look at basically laser drilling. At the beginning was a concept. So this was published in the 90s, where basically we are looking at this as a study of the feasibility of this type of drilling as compared to the traditional one, where you have a mobile truck which will carry the laser and the other tools needed. But as you can predict, this is basically targeting the flexibility of moving around and drilling in other areas without having to move a lot of things as we do now with the standard drilling system. So a laser truck, and then you have, of course, the fiber optic that will deliver the laser at some point down the hole to basically allow access to the oil. So this is a concept. Recently, this is a company based in the US, Colorado and Texas, and this is their first field trial of the laser drilling. But it is a kind of combining laser drilling with mechanical drilling, because laser drilling by itself is still not possible, as I mentioned, due to the laser diameter is not able to cover the large area required. So what they do here is they have a very high power laser that is fed into here, but at the same time you have a mechanical bit that will be drilling. So the laser basically will soften the rock, allowing for faster and more efficient drilling. And you have, of course, here nitrogen supply for basically purging and pushing out the plasma and other particulates. So this is a prototype of the laser that's now being tested. No field trials yet. Maybe they are planned, some of them in Texas soon, but this is what they have. And this is the picture of the laser drill with the bits and the laser basically shining on the rock for testing. So now I will go into the system design. As a system, we will consider then block by block and look at some of the challenges. And we are actually at TII planning to build something in this direction, basically to help into bridging the gap between the research and the technology, and mainly the oil well industry in the region. So looking at the first block, I will not discuss a lot about this. This is mainly for controlling everything. So the whole system must be operated with the control of the current for the laser, voltage, controlling the temperature, the pressure, of course, the mechanical part, so, and safety, and etc. So this is a standard control unit that any system should have. In addition to that, you have the power unit, which supply power to everything. The difference here is mainly for the laser source, which requires very high current, 50 amp or more, and very stable. The power of the laser needs to be very stable, because of the changes in the current will shift the laser wavelength, and sometimes the power will be reduced. The electrical power must also satisfy the needs for the water cooling system and the purging extraction unit. So for the laser source, the high power laser source is now possible with the high power fiber. So the high power fiber allow basically for pumping the laser with many diode lasers between the cladding and the core of the laser. So you have large area or surface where the pumping is happening, and this really spread out the heat. That was a big issue in the beginning, where you're dealing with the laser diode that has very small surface or cavity of the laser, and it gets really hot and not enough space to dissipate the heat. In the fiber optic, you have long fibers that can really dissipate the heat and distribute it over the length and the surface. So this really solved the big issue and provided much higher powers. We can reach now, this is according to one of the leading companies that are producing leaders in the fabrication and marketing of high power fiber lasers, IPG Photonics fibers, and they, as you can see in the graphics here, initially in 1995 it was kind of considered very low power, and almost nobody believed that it will go to much higher power at that time, 1 watt. And then eventually at the time of 2017 or so, we have reached 100,000 watt, which is 100 kilowatt, and I think now they are more than 200 kilowatts. So we are really in a good shape. We have a lot of power, more than enough for laser drilling. So the power is there. This problem of power is really resolved. We have more than enough for application in the oil industry. So this really need to be reconsidered, and many researchers are really working hard on this and developing the other components of the system. The next component is the drilling mechanics and optics. So here we are talking about the beam, the laser beam basically, and the focusing. And in order to drill more and to get more power, you have to focus the beam, but at the same time, focusing will affect the way you drill. So short focusing will give you very shallow holes, while long focusing will give you much deeper holes. In addition to the diameter will be much reduced compared to what is needed for the oil wells. We are really requiring 10 to 20 centimeter diameter, which is far beyond what a laser can give you. If you spread the beam into that diameter, the power will be reduced, power density. So some ideas are applied in certain laboratories, and mainly here we are looking at possibility of rotating the beam using optics, and this will allow the beam to basically span an area, allowing for the drilling to be on a bigger diameter surface. So this is some tentative solutions, but still not yet resolved. The issue here is still not yet resolved, and mainly it involves more engineering and physics, optical engineering, petroleum engineering, mechanical. So this is really a multidisciplinary subject that requires input from many different areas. For the laser matter interaction, now here we are dealing after the laser reach the target material, and what kind of interactions we have. And here we have a lot of physics involved, the interactions between the laser light and the material. So you have a melting temperature that needs to be considered, and we have to remember that the target is not a specific type of material that we can quickly look at the melting temperature. These are rocks which are basically made with different materials, inhomogeneous. We need to be able to optimize the power, and of course we want to avoid cracking. So if you heat it up too much, you may crack the rock, and that is something that we don't want, because we want to be able to seal the hole so that we don't have to use a steel pipe. This is the idea, and where the saving in laser drilling is really important. So there are a lot of innovations that needs to be looked at and considered in this area. Here we are showing some work that was done, showing basically the simulation of the melt. And as the melt flow, the rock is melted, and as the melt flow up, because we are pushing with the gas, the melt eventually cover the surface of the drill, which makes it hard as a ceramic cover to recast the pipe and seal it basically. But there are issues, because this melt, as it goes up, it makes the diameter smaller at some points because it cools down quickly, and this is some issues that still are being studied at this point. Here is mainly the area looking into the basically the efficiency of the laser. Is it CW or pulse laser that will give us the best performance? And recent work really showed that using just in 2019, it shows that really the pulse laser can be better for this type of drilling because it can be controlled more, and therefore we can have much better drilling and more precise breaking and melting of the rock. This is the current solution that is being applied by Foro Energy company, where they are using a smaller drill bit, mechanical one, that will be rotating as a standard one, but they are attaching to it a laser that will rotate and basically make the laser will make the rock softer and easier to drill, and therefore the drilling will be much faster and also less costly. Looking at the traditional drilling, in order to break the rock mechanically, you need to put about 9 tons on the drill bit at the top to push it down to get enough torque to really break the rock. So this is a lot of weight, and doing the drilling and moving with this much weight from one side to another side is very costly. As opposed to this type of drilling, using laser drilling, is almost 20 times smaller. It's about 0.45 ton. You don't need a lot of weight because the laser already made the rock much softer and easier to drill. So this is really a big advantage that is pursued now, and the company Foro Energy is really ahead in this area, and I'm sure there are many other companies that are considering this, if the market allows, of course, because it's very comparative with the prices. Now, the other part that is required is the Purge system. The Purge system is basically to remove, after you drill, you have a plasma cloud which will be screening the laser. And you know, when the laser is traveling, anything in the path will cause reflection, scattering, and power will be reduced. So this needs to be dealt with, and the idea is to purge this using different techniques, and one of the best techniques used is basically a coaxial gas purging, where you have a cylindrical coaxial container that will send the gas, mostly nitrogen, at a high pressure, pushing all the plasma cloud and everything up and clearing the way to the laser. So this is somewhat resolved and is applied in the field. After that, mainly is the following the process, basically following the drilling process to and optimizing it. So to do that, you need to get several sensors that will work at those temperatures, because we are dealing with very high pressure and high temperature. So the sensors needed for that are rugged and able to perform at those temperatures. So the sensing and inspection to go to feed into the control system and decide on what kind of power needs to be used for the laser to adjust it and to be able to drill with optimum energy. With that, I will proceed to the next slide, where we then have this laser will be used in not only drilling, but there are oil, even the old oil wells that have already been operated. Sometimes you need to do some intervention related to welding or cutting, and these can be performed much easier with the high power laser that has a very small cross section and can penetrate all the way to the target and do the job in a very precise way. So welding, cutting, and well completion are among the other applications in addition to laser drilling. So these interventions for basically repairs is very important as well. So in conclusion, I would summarize mainly the points that I discussed here. Progress in power of laser has been achieved. In fact, we have more power than we need in laser drilling. So this is accomplished. Laser heating issues are partially resolved. And this is due to the development of high power fiber lasers. This really limited and allowed us to avoid dealing with the high temperature by spreading the laser power over long distances of the fiber and not letting it be concentrated on a very small area. And the cooling then is reasonable, required only some reasonable cooling. The gas purging issues are resolved, but of course require a lot of gases to be used. As you drill, you have to continuously purge with the gas, but as the standard drilling, you also need to purge, except that in standard drilling, the water is available in generally, more so than compressed air. So there is some cost involved in that. Drilling bigger holes, diameters, this is still a challenge. And a lot of research is open in this area. And definitely there are different methods combining different ideas, but it's still not completely resolved by drilling only with laser. Mainly at this point we are using, or at least some companies are using, a hybrid between laser and mechanical drilling. Other issues that are going to be, or at least are ongoing and being considered, is the use of laser in the presence of fluids, as this is something that will eventually have to be dealt with if you are going to be drilling in the sea wells. You will have to consider how to deal with the laser basically in the presence of the drilling fluids. If you are using mechanical drilling, also you need to deal with that. So this is something that is still ongoing. Laser drilling also eliminates the casing, the steel well casing, so you don't need to use that, which is a big saving regarding the traditional drilling methods. The efficiency of post laser is under investigation, but some recent research shows that post lasers are actually more efficient in drilling lasers, especially with the high power that is now available. And of course, the technology transfer and innovation is providing many opportunities in this area. So it is really a good time to investigate in this area and really bridge the gap between the fundamental research and laboratory research and the technology transfer to the industry. So more field tests are still needed, and that's the last stage basically. After the technology is matured, we generally conduct several field tests. Right now there are only very few field tests planned, so this is something that is going to be done in the very near future in many areas around the world, especially with the companies developing the laser technology for drilling. The cost is something related to the market, of course. So more demand, of course, then the prices and the cost may be driven lower, and be more competitive with the regular standard drilling. With this, I conclude my presentation and hopefully give a general ideas about where we are now with laser drilling and what is the next challenge to consider in this area. Thank you.
Thank you very much. Thank you very much, Dr. Bouchalkh. Any questions? I have one question. What is the typical ablation rate? How distance of we can drill? We use, for example, 20 kilowatts during
around 20 kilowatt is what is considered the minimum, because of the loss due to the fiber. Remember, we have to consider sending the power long distance. So with the fiber optics losses, now with the better optical fibers, we can have a good efficiency. But starting with 20 kilowatt laser, fiber laser is the minimum. And we have a lot of power now.
Thank you very much.